In precisely 48 hours, an extraordinary event will unfold, meticulously prepared for by NASA. An entity hurtling at 137,000 miles per hour from an alien star system is set to approach within 29 million kilometers of Mars. However, there's a crucial detail they're withholding. Avi Loeb, a prominent figure from Harvard, has assessed this object as a 6 out of 10 on his scale for potential extraterrestrial technology, indicating a 60% probability that it is not a natural phenomenon. Once you witness what amateur astronomers have recently captured photographically, you'll comprehend the profound bewilderment gripping the scientific community. This object exhibits behavior unlike any comet ever encountered. It is expelling pure nickel devoid of iron, a process deemed impossible in nature and indicative of industrial manufacturing. Its chemical composition is 16 times more extreme than any known comet, and it transformed from a reddish hue to green overnight. Furthermore, its trajectory possesses a mere 1 in 500 chance of being random. The situation takes a chilling turn in late September when Three-Eyed Atlas vanishes behind the Sun for a period of 2 months, rendering it unobservable during its closest approach to Mars on October 30th. Loeb suggests this concealment could be deliberate, designed to evade detection when it is at its brightest or when another event transpires. Some scientists posit that it may have already deployed imperceptible precursor probes, too small for Earth-based telescopes to detect, which could reach Mars while our attention is fixated on the primary object. Over 227 observatories globally have been tracking this phenomenon, compiling more than 4,000 observations, each data point further deepening the enigma. With a mass estimated at 33 billion tons, its existence defies current scientific understanding. The mathematical probability of encountering such a colossal object before finding 100,000 smaller ones is virtually nil. This raises the paramount question: what exactly is Three-Eyed Atlas? In the ensuing hour, I will unveil every anomaly, every leaked observation, and every theory that scientists are reluctant to publicly discuss. Because following October 3rd, when the Martian spacecraft direct their cameras toward this entity, we may finally find answers, or perhaps uncover something far more disconcerting. If this captivates you as much as it does me, please engage the like button, subscribe, and share in the comments your current location, the local time, and the most peculiar incident you've ever experienced. Chapter 1. Avi's Astonishing 6 out of 10. Assessment. Avi Loeb has just taken an action, sending shockwaves through the astronomical world. The Harvard astrophysicist who previously speculated on the possibility of Oumuamua being alien technology in 2017 has now assigned Three-Eyed Atlas a 6 out of 10 rating on his scale for potential technological origins, signifying a 60% confidence that it is not a natural occurrence. Before dismissing this claim, understand the data that has swayed his opinion. It wasn't conjecture, but rather empirical evidence from the James Webb Space Telescope, the Very Large Telescope in Chile, and Hubble, all revealing phenomena that defy natural explanations. Webb observed Three-Eyed Atlas on August 6th, determining that its gas plume consisted of 95% carbon dioxide and only 5% water, a ratio 16 times more extreme than any known comet at that distance from the Sun. Comets are expected to be water-rich, but this object is not. Subsequently, the VLT detected nickel within the gas plume, evidenced by strong, clear emission lines, yet crucially, no iron. In the entire history of observing celestial bodies, nickel and iron have always been detected together, forged in dying stars and dispersed together during supernovas. The presence of nickel without iron would be analogous to smoke without fire. It simply does not occur naturally but is commonplace in industrial manufacturing, such as in high-purity nickel alloys and aerospace components. The chemical signature aligns with factory production, not cosmic debris, and the nickel output is escalating. Initially detected in July, the emission rate was modest, but by August, it had increased 25-fold. As the object draws nearer to the Sun, it vaporizes more metallic material. Loeb has faced severe backlash for even suggesting extraterrestrial hypotheses. Jason Wright of Penn State characterized his work as careless, while NASA's Tom Statler maintained that it appears to be a comet behaving like one. However, neither has provided an explanation for the nickel detected without iron, nor have they addressed the extreme carbon dioxide ratio or the trajectory with its 1 in 500 chance of being random. Loeb himself acknowledges that his technological hypothesis is largely an exercise, conceding that a natural comet remains the most probable explanation, though most likely does not equate to certainty. With a 6 out of 10 rating, he suggests there's a 40% possibility that our current understanding is fundamentally flawed. The close encounter with Mars on October 3rd will provide further clarity. If the high-rise camera reveals a nucleus exceeding 5 kilometers in diameter, as his mass calculations suggest, the natural explanation will be definitively disproven, as there is insufficient rocky material in interstellar space to account for objects of such magnitude appearing with this frequency. Chapter 2. The amateur photograph that went viral. Social media is abuzz with observations that professional astronomers are hesitant to address. Amateur astrophotographers are sharing images of three-eyed Atlas that deviate significantly from the typical appearance of a comet. Instead of the expected diffuse glow, some photographs exhibit structure, geometric forms, and sharp edges that are inconsistent with natural phenomena. Michael Jagger and Gerald Raymond, two highly esteemed amateur astronomers, captured three-eyed Atlas during the total lunar eclipse on September 7th from Namibia. Their images depicted the object emitting a green glow with a bluish tinge, clearly indicative of a gas-rich composition, and visible in both blue and green filters. While professional astronomers have validated these images as authentic, it is the contributions from other amateurs, whose names have not been publicized, that have led to what is now being referred to as the structured images. These photographs, circulating across Reddit, Twitter, and various astronomy forums, suggest a more solid, defined form beneath the gaseous envelope, appearing less like a diffuse cloud and more like an object with discernible edges. The professional response has been either silence or immediate dismissal. When pressed, they cite factors such as motion blur, exposure artifacts, and telescope tracking inaccuracies, all valid concerns when imaging rapidly moving objects at immense distances. However, the intriguing aspect is this. The Atlas Survey Telescope, which discovered three-eyed Atlas, is only 20 inches in diameter, comparable to equipment used by amateur astronomers. When individuals with similar instruments capture unusual structural details, why is there an automatic dismissal without thorough investigation? Debates are intensifying on Reddit's astronomy subreddits, with users comparing images side by side. Some display the classic cometary appearance with a developing coma and faint tail, while others present phenomena that are more challenging to explain, such as compact cores, irregular shapes, and pixel patterns inconsistent with standard point spread functions for stars or comets. Approximately half of the commenters attribute these anomalies to image processing errors, while the other half are demanding that professionals with more sophisticated equipment replicate the observations for verification. This replication is not occurring. Instead, professional astronomers are entering discussions to discredit the findings without offering to conduct their own investigations. One widely shared image on X appears to show a more compact, less diffuse core than that captured by Hubble. The amateur photographer claimed it was taken with a 14-inch Schmidt-Cassegrain telescope, stacking 50 individual exposures, a standard practice for deep sky imaging. Professional astronomers were quick to attribute the observed features to atmospheric distortion, tracking drift, or chromatic aberration, offering various explanations to dismiss the anomaly. Yet none suggested using larger telescopes to examine the same coordinates, nor did they offer assistance in verifying the observation. Instead, there was only dismissal. This situation is peculiar because the Hubble Space Telescope image from July 21st showed a teardrop-shaped dust cocoon with the glow extending forward of the object towards the Sun. This official NASA data already contradicted expectations, as comet tails are supposed to stream behind, propelled by solar wind and radiation pressure. This object's tail was pointing forward. Professional astronomers described this observation as interesting, puzzling, and worthy of study. However, when amateurs observe similar anomalies during the same period, it is attributed to user error. Subsequently, Gemini South captured images on August 27th, providing the initial evidence of a proper anti-solar tail streaming behind the object. This indicates that between July and August, something changed. Either Three-Eyed Atlas began to behave more like a conventional comet, or our viewing angle shifted sufficiently to reveal what had always been present. A significant portion of the amateur photographs claiming unusual structure were taken during that July to August timeframe, when the object was exhibiting the least cometary behavior, and even professional observations revealed anomalies. An additional, often overlooked data point comes from NASA's SPECS Infrared Space Telescope, which observed Three-Eyed Atlas in early August and detected it as a point source with no extended coma or tail, simply a dot. This is not how comets appear in infrared. They typically display extended emission from warmed gas and dust. SPECS, however, registered nothing of the sort, only a singular bright point. Thus, a pattern emerges. Professionals observe anomalies they cannot fully explain, while amateurs observe anomalies that are dismissed as incompetence. Both are photographing the same object during the same peculiar window when it was not behaving like a comet. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are scheduled to photograph Three-Eyed Atlas on October 3rd, utilizing cameras designed for imaging the Martian surface from a distance of a few hundred kilometers. They will be imaging this object from a distance of 30 million kilometers. ESA has already stated that spectacular images are not anticipated, as the object will appear as less than a single pixel in their cameras. However, what if the amateurs were indeed observing something tangible? What if there is an underlying structure beneath the gas? The October observations may not resolve this either. A closer approach with more advanced instruments, directly focused on this object without atmospheric interference, might be necessary. The reality is that we are operating with limited information. Professional telescopes have restricted observation time and predefined schedules, while amateurs possess flexibility but less sophisticated equipment. Somewhere within this disparity, something unusual is occurring that neither side is fully prepared to acknowledge. Because if the amateurs are correct, and there is structure that does not conform to natural cometary morphology, then we are not merely discussing imaging artifacts. We are contemplating a fundamental revision of our understanding of interstellar visitors. Chapter 3. The October 3rd Mars Encounter. What They're Not Telling You. In 2 days, Three-Eyed Atlas will pass within 29 million kilometers of Mars. While this sounds like a considerable distance, the critical detail being omitted is that the minimum orbit intersection distance, the closest this object comes to Mars' complete orbital path around the Sun, is a mere 2.7 million kilometers. Avi Loeb has termed this a remarkable fine-tuning, and when a Harvard physicist uses such precise language, it warrants significant attention. The high-rise camera aboard the Mars Reconnaissance Orbiter will capture images of Three-Eyed Atlas on October 3rd with a resolution of 30 kilometers per pixel, which is sufficient detail to distinguish the nucleus from its surrounding dust cloud, measure the actual surface area reflecting sunlight, and confirm whether this object truly measures 5 kilometers in diameter, as suggested by Loeb's latest mass calculations. If it is indeed that large, the natural comet explanation will completely disintegrate. Based on the limited reservoir of rocky material in interstellar space, we would expect to have detected approximately 100,000 smaller interstellar objects, similar in scale to Oumuamua, before encountering something as massive as Three-Eyed Atlas. Yet, we have only identified 2 previous visitors, both considerably smaller than this object. However, the situation takes a truly disturbing turn. Loeb has calculated that if Three-Eyed Atlas were to deploy a precursor probe, a smaller scout craft traveling approximately 30 million kilometers ahead of the main object, that probe could reach Mars on October 3rd or during the preceding week. The terrifying aspect is that Earth-based telescopes are incapable of detecting objects smaller than roughly 100 meters at Martian distances, which is approximately the size limit of all spacecraft humanity has ever launched. Consequently, any precursor probe would be effectively invisible to us. This concept is not as far-fetched as it might seem. If one were designing an interstellar mission to survey a planetary system, the logical approach would be to send a primary vessel accompanied by smaller reconnaissance probes. These probes would be deployed in advance to gather data on individual planets, while the main craft follows a safe trajectory. This is precisely how such a mission would be designed if the technology were available. The trajectory of Three-Eyed Atlas renders this scenario disturbingly plausible. The object's path would necessitate only a velocity adjustment of 10 to 15 kilometers per second during September to reduce its closest approach distance to Mars to 0. For a technological entity, this is a negligible maneuver, but for a natural comet, it is impossible. The ejection speed of sublimating icy fragments from comets, based on Webb telescope data, is only approximately 0.4 kilometers per second, which is insufficient. NASA's Mars Express and ExoMars Trace Gas Orbiter will also observe Three-Eyed Atlas on October 3rd, employing multiple instruments including high-resolution cameras, spectrometers, and particle sensors. While these instruments are designed to study the Martian surface and atmosphere, they are being repurposed to investigate this visitor. The instruments will aim to characterize the comet's volatile activity and composition from a distance of 30 million kilometers. However, there is a secondary objective that is not being publicly advertised. The orbiter will not only image Three-Eyed Atlas itself, but will also scan the surrounding space for any entities potentially traveling ahead of the main object, searching for precursor probes. Loeb explicitly suggested this in his blog posts. Utilizing HiRISE to search for objects preceding Three-Eyed Atlas that approach Mars more closely than the main body. If materials from Three-Eyed Atlas reach Mars in October through mechanisms that could not occur via natural sublimation and ejection, that would serve as a definitive signature of technology. The timing is also highly suspicious. Three-Eyed Atlas reaches its closest approach to Mars exactly 1 week before it disappears from Earth's perspective behind the Sun. We will have one opportunity for a detailed observation by spacecraft at Mars, after which the object will be obscured by solar glare for 2 months, becoming observable again only in early December. If the objective were to deliver something to Mars undetected, this would represent the ideal window. Deploy the probe during the October 3rd flyby, while Earth-based telescopes focus on the primary object, and then have the mothership conceal itself behind the Sun for 8 weeks while the probe carries out its mission. NASA's Curiosity and Perseverance rovers on the Martian surface may also attempt observations. Although the comet will be exceedingly faint from the surface perspective, the Mars Reconnaissance Orbiter remains our most promising tool for detailed imaging. Furthermore, there is the critical question of what happens if something is discovered. If HiRISE captures an image revealing multiple objects, unusual maneuvering, or any indication of artificial activity, what is the established protocol? Will it be announced immediately? Will it undergo verification through additional observations? Will it be classified? There is no established procedure for such a scenario because no one has seriously anticipated it. Existing protocols for detecting extraterrestrial intelligence primarily focus on radio signals or optical beacons, not physical craft traversing the inner solar system. Within 24 hours, we will ascertain whether the amateur astronomers were observing a genuine phenomenon. We will learn whether the nickel without iron signature carries the significance that Loeb believes. We will discover if the 2.7 million kilometer minimum orbit intersection distance was a coincidence or intentional design. Alternatively, we may witness the observation of a perfectly ordinary cometary nucleus consistent with natural formation, leading to the complete collapse of all speculation into embarrassment. Regardless of the outcome, October 3rd, 2025, may well be a date etched in history books, the day we either confirmed Three-Eyed Atlas as an exotic yet natural interstellar comet, or the day everything fundamentally changed. Chapter 4. The Nickel Without Iron Revelation. The Very Large Telescope in Chile has just made a detection that defies natural explanation. Between late July and late August of 2025, spectroscopic analyses revealed the presence of neutral nickel atoms emanating from Three-Eyed Atlas. These were indicated by strong emission lines across multiple wavelengths, providing clear and unambiguous evidence of nickel sublimating from the object's surface as it approached the Sun. However, no iron was detected. There was not a single trace, meaning zero emission lines in any of the expected wavelengths where iron should have been present. To fully grasp the shock value of this finding, consider this. Nickel and iron are intrinsically linked in the cosmos. They are formed together through the same nuclear reactions within massive stars. When these stars undergo supernova explosions, nickel and iron are expelled into space as a unified entity. They then condense into dust grains collectively and are incorporated into asteroids and comets as a pair. In every single celestial rock sample that humanity has ever analyzed, whether meteorites found on Earth or samples retrieved from space missions, nickel and iron consistently appear in predictable ratios. The detection of one element without the other would be akin to finding hydrogen devoid of protons. It fundamentally violates the established chemistry of the universe. The Very Large Telescope research team, comprised of scientists unconnected to Avi Loeb's more controversial assertions, published their findings with carefully phrased conclusions. They proposed that the nickel might originate from nickel-carbonyl compounds, molecules that could theoretically persist in extremely frigid interstellar environments. These compounds are volatile and are known to break apart when exposed to ultraviolet radiation, releasing nickel and carbon monoxide. However, even the VLT team acknowledged that this would be an unprecedented occurrence, never before observed in any solar system comet or detected in interstellar space, a purely theoretical explanation for an observation that demands one. The situation is further exacerbated by the fact that the nickel production is not static. When Three-Eyed Atlas was initially observed at a distance of 3.9 astronomical units from the Sun in July, the nickel emission rate was approximately 10 to the 21st, which, while significant, was not alarming. By late August, at a distance of 2.85 astronomical units, that rate had increased by a factor of 25. 25 times more, nickel was streaming from the surface in just 1 month. The closer the object gets to the Sun, the more dramatically its metallic emissions intensify. This increase does not follow the gradual curves observed with typical cometary outgassing. It is exponential and steep, suggesting something is being systematically vaporized by increasing heat. Avi Loeb highlighted what others hesitated to state explicitly. On Earth, we routinely separate nickel from iron in industrial processes. High-purity nickel is utilized in specialized alloys for aerospace applications, electronics, batteries, and any field requiring specific thermal or electromagnetic properties. The signature detected from three-eyed Atlas mirrors industrial nickel production, not the natural cosmic abundances. Critics immediately seized upon this, accusing Loeb of selectively presenting data, seeking confirmation bias, and engaging in motivated reasoning. Jason Wright of Penn State was particularly scathing, labeling the comparison to industrial processes as misleading and unscientific. However, the critics failed to address a critical point. If the nickel originates from natural carbonyl compounds, where is the iron? Iron forms similar volatile compounds. Iron pentacarbonyl, for instance, is well studied in chemistry. If the conditions were conducive to the creation and preservation of nickel carbonyl throughout billions of years in interstellar space, those same conditions would have facilitated the creation of iron carbonyls. Both should be present, yet only nickel is being detected. The VLT observations also indicated a rapid increase in cyanide production, with hydrogen cyanide and related compounds appearing in the gas plume surrounding Three-Eyed Atlas, at rates that steeply increased as the object neared the Sun. Loeb suggested that the observed color change from red to green by amateur astronomers might be linked to this surge in cyanide. While cyanide itself is not unusual in comets, being a common carbon and nitrogen compound found in many icy bodies, the rate of increase, the steep production curve mirroring the nickel emission, suggests a potential interrelationship between these processes. The most compelling aspect of this discovery lies in what it reveals about the object's internal structure. If the majority of its mass consists of frozen carbon dioxide with only minute traces of water as discovered by Webb, and if the surface is emitting nickel and cyanide at escalating rates, we are observing a chemical signature unlike anything formed within our solar system. Comets originating from the Oort cloud or the Kuiper belt are abundant in water because they formed in regions where water ice remained solid. The proportion of water to carbon dioxide reflects the temperature and composition of the primordial disk from which they emerged. Three-Eye Atlas, however, displays the inverse ratio. It is overwhelmingly carbon dioxide with minimal water. This suggests it originated in a vastly different stellar environment, or perhaps it is not a natural celestial body at all. There remains a third hypothesis, one that few are willing to seriously entertain. What if Three-Eye Atlas is indeed a natural ancient comet from another star system, but has undergone significant surface alteration due to its prolonged journey through interstellar space? The cumulative effects of cosmic radiation, collisions with interstellar dust particles, and chemical reactions in the near-absolute zero vacuum over 7 billion years could profoundly change its surface composition. It is conceivable that the observed nickel signature, devoid of iron, is authentic, but the explanation lies somewhere on a spectrum between a natural comet and an artificial craft, a possibility we haven't yet conceived of due to our lack of prior study of such an ancient and distant object. The observations scheduled for October, when the Hayabusa spacecraft images Three-Eye Atlas from Mars orbit, will be invaluable. Furthermore, spectroscopic data from the Mars Express and ExoMars Trace Gas Orbiter missions will capture additional emission lines, providing more information on nickel production, quantifying the cyanide and carbon dioxide outgassing, and thus offering greater insight into the true nature of this entity. However, based on the current data, Three-Eye Atlas is releasing industrial-grade nickel into space without any detectable iron. The scientific community lacks a satisfactory natural explanation for this phenomenon. Chapter 5. The Vanishing Act, Concealed by the Sun. In late September, Three-Eye Atlas disappears from view. It is not destroyed or diverted, merely obscured. From Earth's vantage point, it traverses too close to the Sun to be observed. For a period of 2 months, from late September through November, ground-based telescopes completely lose visual contact. the object vanishes into the overwhelming glare of the sun. What makes this timing particularly suspicious is that 3I Atlas reaches its perihelion, its closest approach to the sun, on October 30th, 2025. This is the period when comets are most active, when solar heating intensifies their outgassing, and when their behavior offers the most revealing insights into their composition and structure. This is the single most critical observation window for understanding the object's true nature. Yet, we are unable to see it. Earth will be positioned on the opposite side of the sun. Avi Loeb has posited that this alignment may not be coincidental, but rather a deliberate maneuver. If 3I Atlas intended to evade detailed observation by Earth-based telescopes during its most luminous and active phase, its current trajectory perfectly achieves this objective, concealing itself behind approximately 150 million kilometers of incandescent plasma at this crucial juncture. NASA and other space agencies are endeavoring to circumvent this observational blackout. The Parker Solar Probe, currently in close solar orbit studying the sun's corona, might capture a fleeting glimpse if its timing is fortunate. The Solar and Heliospheric Observatory, SOHO, which continuously monitors the sun for coronal mass ejections, will have 3I Atlas pass through its field of view. However, SOHO's cameras are optimized for solar observation, not for detecting faint comets. The object is likely to be too dim to be discernible against the sun's overpowering brilliance. The Jupiter Icy Moons Explorer, JUICE, is presently on the far side of the sun relative to Earth. It is utilizing its high-gain antenna as a heat shield, which significantly limits its data transmission capabilities. JUICE will attempt to observe 3I Atlas in November using its cameras and spectrometers, but the data will not be received until February 2026, many months after the event. Consequently, we are effectively blind during the most critical observational period, with October 30th occurring behind a stellar veil. What might transpire during these 2 months? If 3I Atlas is a natural object, nothing out of the ordinary. It will warm up, exhibit increased outgassing, and potentially fragment if thermal stress causes fissures in its nucleus before reappearing in December, slightly diminished in size and activity as it continues its journey back into interstellar space. However, if it is not natural, if any form of technological component is involved, these 2 months represent an ideal window for activities we are not intended to witness. These could include orbital adjustments, the deployment of probes, or trajectory modifications, any maneuver requiring propulsion or steering that would be readily apparent to Earth-based observers if we possessed the capability to see it. Loeb has calculated that a velocity change of merely 10 to 15 kilometers per second during September or October could significantly alter 3I Atlas's trajectory, rendering it capable of delivering payloads to Mars, Venus, or even Earth. For a natural comet, such a maneuver is impossible. The sublimation of ice generates velocity impulses of perhaps half a kilometer per second at most. For an object equipped with an engine, however, such adjustments are trivial. A more unsettling possibility exists. What if the disappearing act is precisely that? What if 3I Atlas fails to reemerge in December? What if it utilizes the perihelion passage to shed velocity, settling into a prolonged elliptical orbit around the sun, thereby becoming a permanent inhabitant of the inner solar system? We would have no means of knowing until December, when it is scheduled to reappear. And if it fails to materialize at the predicted orbital location, if its orbit has substantially changed, this would be a clear indication of propulsion, of technology, of intent. This line of reasoning, while unconventional, finds some precedent, albeit not with interstellar objects. In 1986, the Soviet Vega probes flew past Halley's Comet and detected an unexpected anomaly. The nucleus was significantly darker than anticipated, reflecting only 4% of incident sunlight. Prior to the Vega missions, scientists generally assumed comets to be bright, icy bodies. It transpired that they are remarkably dark, coated in organic compounds and dust, with the ice concealed beneath a hardened surface layer. This discovery fundamentally altered our perception of comets at close range, and it was achieved through direct spacecraft observation. Remote observation from Earth had led to entirely erroneous assumptions. With 3i Atlas, we are once again reliant on remote observation during a critical period, inferring behavior from limited data and making assumptions that could prove to be profoundly incorrect. We will not have definitive answers until December 3rd, when it emerges from behind the Sun and once again becomes visible to ground-based telescopes. Amateur astronomers are already preparing, with telescopes worldwide being scheduled for early December observations. Everyone is eager to be the first to witness its return. Everyone wants to ascertain if it appears different, if its activity level has changed, or if its trajectory aligns with predictions. Because if it deviates from expectations, if 3i Atlas emerges from perihelion on an altered path or with modified characteristics, the mainstream astronomical community will be compelled to seriously consider the artificial hypothesis, not as a fringe theory advanced by a single controversial scientist, but as a legitimate possibility warranting thorough investigation. The Disappearing Act also prevents us from observing potential fragmentation events. Natural comets occasionally break apart near their perihelion due to thermal stress fracturing the nucleus or internal pressure from trapped volatiles expelling material from the surface. We have witnessed this phenomenon with several comets that ventured too close to the Sun. If 3i Atlas fragments, we will not observe the event itself, only its aftermath in December. Multiple pieces instead of a single entity, trailing debris, and altered rotation. Fragmentation would, in fact, lend support to the natural comet hypothesis, as technological objects do not typically disintegrate due to solar heating. However, this assumes the fragmentation is not controlled, and that what we interpret as a breakup is actually a deliberate deployment, with multiple smaller objects separating from the main body, each destined for different targets within the inner solar system. Such a scenario might sound like science fiction, but so does the presence of nickel without iron, the precise alignment with the ecliptic, and the remarkably precise flyby of Mars with an accuracy of 2.7 million kilometers. Each piece of collected data progressively transforms these science fiction scenarios into increasingly plausible possibilities. The reappearance in December will undoubtedly yield significant insights, perhaps not definitive answers, but something. Until then, we remain in darkness, hoping that the object that returns is the same one that disappeared behind the Sun. Chapter 6. The Anomalously Massive Object. 33 billion tons. A new research paper has been published, causing considerable discomfort among astronomers. Richard Chloe, Peter Vey, and Avi Loeb have analyzed 4,022 observations of 3i Atlas, gathered from 227 observatories worldwide between May 15th and September 23rd. They meticulously tracked the object's position, comparing its actual trajectory with the path predicted by gravitational forces alone. Their findings were astonishing. 3i Atlas exhibits virtually no non-gravitational acceleration. Despite extensive outgassing detected by Webb and other telescopes, and despite losing hundreds of kilograms of material per second, the object's trajectory deviates by less than 15 meters per day, squared from a path governed solely by gravity. This implies an extraordinarily high mass, far exceeding what its luminosity would suggest. The underlying physics are straightforward. When a comet releases gas, the expelled material acts as a minuscule rocket engine, imparting a slight push that alters the comet's course. The magnitude of this deviation depends on the volume of expelled mass and the comet's total mass. Small, actively outgassing comets display significant non-gravitational acceleration. Conversely, large comets with the same rate of outgassing exhibit less deviation. 3I Atlas is expelling substantial quantities of gas. Webb measured 129 kilograms per second of carbon dioxide, 6.6 kilograms per second of water, and 14 kilograms per second of carbon monoxide. These are significant figures, which should result in noticeable trajectory changes. Yet they do not. The deviation remains below detection limits, indicating that the object's mass must be immense to resist this propulsive effect. Calculations place the lower limit at 33 billion tons, or 33 trillion kilograms, with a nucleus diameter of at least 5 kilometers. This renders 3I Atlas 3 to 5 orders of magnitude more massive than the two previously identified interstellar objects. Oumuamua was perhaps a few hundred meters across at most, and Borisov was approximately a kilometer. This object is 5 times larger in diameter, translating to over 100 times greater volume and mass. The crux of the problem lies in the following. Based on our current understanding of interstellar space and surveys of the abundance of rocky and icy material between stars, objects of such immense size should be exceedingly rare. They should be so scarce that we would expect to detect roughly 100,000 smaller interstellar visitors before encountering one as massive as 3I Atlas. Yet, we have only detected 2 such objects in all of human history. This is akin to winning the lottery 3 consecutive times. Statistically possible, but so improbable that it compels one to question the fairness of the game. Loeb argues that this statistical anomaly suggests a non-random trajectory. If 3I Atlas was deliberately directed toward the inner solar system, if its path was chosen rather than being a result of random chance, then the statistical problem effectively disappears. We are not sampling the interstellar population randomly. Rather, we are being visited by something specific. Critics dismiss this assertion as preposterous, pointing to the dramatic improvements in our detection capabilities in recent years. The Atlas survey that discovered 3I Atlas only became fully operational within the last decade. Prior to this, our efforts to detect such objects were far less thorough. It is therefore unsurprising that we are now finding more interstellar objects as we finally possess telescopes capable of spotting them. This is a valid point. The Vera C. Rubin Observatory, which became operational in 2025, identified over 2,000 asteroids within its first 10 hours of operation. Our ability to detect faint, fast-moving objects has undergone a significant explosion. It is plausible that we will discover dozens more interstellar visitors in the coming years, thereby resolving the statistical anomaly. However, this does not account for the mass. Even with enhanced detection capabilities and the discovery of more interstellar objects, the size distribution should still conform to predictions. A preponderance of small objects, fewer medium-sized ones, and very few large ones. This pattern holds true across all other areas of astronomical observation. Small asteroids vastly outnumber large ones by millions to one. 3I Atlas defies this established pattern. It is by far the largest object we have discovered, and it was identified before we have catalogued the thousands of smaller objects that should be more common. Furthermore, the absence of non-gravitational acceleration rules out certain explanations. Some scientists have proposed that 3I Atlas might be a loosely bound aggregate of debris, held together by weak gravitational forces. If this were the case, the process of outgassing would cause it to disintegrate. The forces exerted by the released gas would overcome the gravitational binding, leading to fragmentation. However, the object is not fragmenting. It is maintaining its structural integrity despite substantial mass loss. This requires either a solid, coherent nucleus or a binding force more potent than self-gravity. The observations from Mars in October may help clarify the size issue. If the Hayabusa spacecraft can differentiate the nucleus from its surrounding dust cloud and measure the amount of light reflected from the solid surface versus that scattered by intervening particles, we will obtain a more precise estimate of the actual nucleus diameter. If it exceeds 5 kilometers, the natural explanation becomes untenable. There is another possibility that has received little attention. What if 3I Atlas is enveloped in a vast, diffuse cloud of extremely fine dust, and the majority of the visible brightness originates from this dust rather than the nucleus itself? In such a scenario, the nucleus could be considerably smaller, rendering the mass calculations inaccurate. However, observations by Webb and SPECS, conducted in the infrared spectrum, penetrate dust to reveal underlying solid surfaces. SPECS detected 3I Atlas as a point source, not an extensive cloud. This suggests that there is no enormous dust envelope obscuring a small nucleus. Consequently, what we are observing is predominantly the object itself. We are thus left with a 5-kilometer nucleus possessing a mass of at least 33 billion tons, exhibiting almost no non-gravitational acceleration, despite significant outgassing. This is an object that, statistically speaking, should not exist, arriving on a trajectory with only a 1 in 500 probability of being random. The accumulated data continues to mount. Each new observation renders the natural explanation increasingly unconvincing. It is not impossible, but it requires progressively more convoluted reasoning, an accumulation of coincidences, and a series of unprecedented conditions. Chapter 7. Chemical Impossibilities, the 95% CO2 Mystery. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, utilizing its near-infrared spectrograph. The findings have fundamentally reshaped our understanding of what interstellar comets should resemble. The gaseous plume surrounding 3I Atlas is composed of 95% carbon dioxide and only 5% water. This ratio is 16 times more extreme than what is typically expected for a comet at that distance from the Sun. Every comet we have ever studied originating from our solar system is rich in water. They formed in the frigid outer regions where water ice was the predominant volatile compound. Carbon dioxide is present, but in significantly smaller quantities. This ratio serves as an indicator of the temperature and chemistry of the protoplanetary disk from which they originated. 3I Atlas, however, exhibits the inverse chemistry. It is essentially a dry ice ball with a negligible amount of water. This suggests it formed in a drastically different environment, around a star with a distinct composition, within a disk characterized by different temperatures and pressures, an environment utterly unlike the formation conditions of our own solar system. Martin Cordner, the lead investigator for the Webb observations, stated, "This represents one of the highest carbon dioxide to water ratios ever measured in any comet. It is not merely unusual, it is unprecedented." The chemical peculiarities, however, extend further. Webb also detected significant quantities of carbon monoxide and carbonyl sulfide. The co-occurrence of these compounds indicates that the object likely formed in an extremely cold environment, possibly colder than the outermost reaches of our solar system. Some researchers hypothesize that 3I Atlas may have originated in a molecular cloud region or been ejected from a planetary system situated much farther from its star than our Kuiper belt. Adding to the enigma is the color change documented by amateur astronomers. During July and early August, observations revealed 3I Atlas, possessing a reddish coma. This coloration typically signifies the presence of organic compounds, complex carbon molecules that absorb blue light and reflect red light, a common characteristic of comets. However, on September 7th, during a total lunar eclipse, Michael Jagger and Gerald Raymond captured images of it glowing a vibrant green with a bluish tinge. This transformation appeared to occur almost overnight. Green comets are a well-known phenomenon, with the color arising from diatomic carbon molecules in the coma absorbing ultraviolet sunlight and re-emitting it as green light. Curiously, 3I Atlas had already been analyzed in August by astronomers at the Kitt Peak Observatory. They determined it to be among the comets with the lowest carbon chain depletion known, possessing very low concentrations of diatomic carbon, the precise molecule responsible for the green coloration in comets. So, how does a comet with virtually no diatomic carbon suddenly exhibit a bright green glow? Avi Loeb has proposed that the color change might be linked to the rapid increase in cyanide production detected by the Very Large Telescope. Cyanide compounds can also produce greenish hues under specific conditions. But this raises yet another question. Why is cyanide production escalating so dramatically? Observations from the VLT indicated a steep rise in hydrogen cyanide emission as 3I Atlas approached the Sun. The production rate was not a gradual increase, as typically observed with cometary outgassing, but rather an exponential surge, suggesting some form of thermal processing occurring at accelerating rates. Stephanie Milam from NASA's Goddard Space Flight Center, who participated in the Webb observations, suggested that 3I Atlas might possess a cooked shell. Billions of years of travel through interstellar space, exposed to cosmic rays and stellar radiation, could have chemically altered its surface layers. Carbon dioxide might have been synthesized or concentrated through these processes, resulting in its unusual surface chemistry. This is a plausible hypothesis, as we have never studied an object of such antiquity. 7 billion years predates our entire solar system. It is difficult to ascertain the effects of such extended exposure on ice in the near absolute zero void between stars. However, this explanation does not account for all the observed anomalies. The signature of nickel without iron remains unexplained by surface processing. Neither does it explain the lack of substantial outgassing. While each anomaly might possess a natural explanation individually, their collective presence forms a pattern that is increasingly challenging to dismiss. Furthermore, the SPECS observation, which depicted 3I Atlas as a point source devoid of extended emission, is noteworthy. Infrared telescopes can penetrate dust to reveal the thermal radiation emanating from warmed ice and rock. SPECS should have detected a diffuse glow from carbon dioxide ice sublimating across the surface. Instead, it observed a distinct point, a concentrated source of infrared emission consistent with a relatively compact solid object. This observation contradicts the conventional model of a comet, or it suggests that the object possesses highly unusual thermal properties. Perhaps its surface is exceptionally reflective, deflecting sunlight before it can penetrate and heat the interior. Alternatively, there might be an insulating layer preventing heat absorption. It is also possible that the nucleus is spinning so rapidly that thermal energy is distributed before significant sublimation occurs. Or the outgassing might not be occurring as we currently understand it. Perhaps what we interpret as sublimation is something entirely different. The chemical data also provides clues about 3I Atlas's potential origin. Its low metallicity and high hydrogen and ice content suggest it originated from a region of the galaxy characterized by early star formation, such as the thick disk of the Milky Way, populated by older stars with less enrichment of heavy elements. Current estimations place its genesis between 7 and 11 billion years in the past, suggesting it's a remnant from an era when our galaxy was vastly different. Should 3 Atlas prove to be a natural phenomenon, it represents a time capsule from a primordial cosmos. It's a fragment of primeval ice, carrying chemical imprints from epochs predating Earth's very existence. This alone would elevate it to the status of the most scientifically significant discovery ever made. However, its chemical composition presents a perplexing puzzle. While the prevalence of carbon dioxide can be accounted for, as can the scarcity of water, the presence of cyanide, and the observed color shifts, Each individual anomaly offers a plausible, albeit stretched, natural explanation that doesn't fundamentally break our current models. The true enigma lies in their confluence. It's the co-occurrence of these anomalies within a single object, the sheer statistical unlikelihood of this specific combination of characteristics arising by chance. The months of November and December promise further insights. As 3 Atlas reappears from behind the Sun, terrestrial observatories will gather new spectral data, identifying additional emission lines and chemical signatures, thereby refining our understanding of its composition. By comparing its chemistry before and after its passage near the Sun, we will ascertain whether solar heating has induced any fundamental alterations in its behavior. Chapter 8. The anti-tail that should not be. The Hubble Space Telescope captured the most detailed image of 3 Atlas on July 21, 2025. The resulting observation defied fundamental principles of cometary physics. The image depicted a teardrop-shaped envelope of dust, yet the illumination extended forward from the object towards the Sun rather than trailing behind. Notably absent was a distinct tail streaming away from the Sun in the opposite direction. This orientation is counterintuitive. Cometary tails are typically propelled away from the Sun by solar winds and radiation pressure, always pointing away and creating the characteristic swept-back appearance. 3 Atlas, however, presented its illuminated face towards the Sun, devoid of any apparent trailing tail. Jav Loeb and his colleague Eric Quito published the sole scientific paper attempting to explain this peculiar anti-tail phenomenon. They posited that the forward illumination might be attributed to dust particles being expelled ahead of the nucleus by some internal mechanism, though they themselves acknowledged the speculative nature of this hypothesis. No established natural process readily explains a forward-facing dust cloud on a typical comet. Other astronomers dismissed the observation outright, attributing the glow to an artifact of Hubble's tracking system as it compensated for the fast-moving object. The telescope's motion to follow 3 Atlas across the sky, they argued, could cause background stars to streak in the exposure, potentially mimicking a forward glow. However, Hubble's image processing specialists are adept at accounting for such tracking effects. The streaks, indicative of tracking motion, are clearly discernible in the image, whereas the forward glow exhibits distinct structure and defined boundaries, unlike a mere streak. If it were a tracking artifact, it would mirror the appearance of the stellar trails. This is not the case. Subsequently, in late August, the Gemini South Telescope acquired new images utilizing its multi-object spectrograph. Astonishingly, 3 Atlas had by then developed a discernible tail, a faint, teardrop-shaped formation extending backward from the object, precisely in the expected cometary tail direction. This evolution between July 21st and August 27th suggests a significant change. Either the object began behaving like a conventional comet, or our observational vantage point shifted sufficiently to reveal features that were previously obscured by the dust cloud. The July Hubble image was captured when 3 Atlas was approximately 4 astronomical units from the Sun. The August Gemini image was taken at roughly 2.6 astronomical units. Proximity to the Sun implies increased solar heating, heightened outgassing, and consequently, potentially greater dust production. It is conceivable that the tail had not yet fully formed in July and subsequently appeared as the object's activity intensified. However, this still fails to account for the forward illumination. Conventional comets do not exhibit bright halos directed towards the Sun. Instead, they possess comas, spherical envelopes of gas and dust surrounding the nucleus. While the sunward side of a coma can be brighter due to more active sublimation, it should not produce a directional glow ahead of the object's trajectory. Another perplexing detail within the Hubble image concerns the dust envelope, which extends approximately 3,000 kilometers in all directions from 3 Atlas. Loeb's calculations indicated that if the nucleus were 10 kilometers in diameter, the dust density at a distance of 3,000 kilometers would be diminished by a factor of 90,000 relative to its surface density. Such a drastic dilution makes it improbable for the dust to remain sufficiently luminous for Hubble to detect. This implies either an extraordinary rate of dust production, exceptionally reflective dust particles, or an unusual scattering geometry. The Gemini images also revealed variations in color. Different wavelength filters highlighted distinct structural features. In the ultraviolet spectrum, the object appeared more compact. In red and infrared wavelengths, the dust cloud was more expansive. This aligns with typical dust scattering properties, where smaller particles preferentially scatter blue light and larger particles scatter red light. It also suggests a non-uniform distribution of dust grain sizes, with a population of very fine particles close to the nucleus and larger particles further out. This size distribution pattern could provide insights into the dust ejection mechanism, with fast-moving fine particles and slower-moving larger particles, consistent with classic cometary behavior. However, the object's rotation period introduces complications. Observations indicated that 3 Atlas rotates once every 16 hours, a relatively slow rate for an object of its presumed size. A 10-kilometer nucleus rotating every 16 hours possesses an equatorial surface velocity of only about 1 meter per second. This speed is insufficient to eject dust particles into space through centrifugal force. Consequently, the dust must be expelled by gas pressure originating from sublimation. Carbon dioxide sublimating on the sunward side would carry dust grains with it. Yet, the analysis of the Hubble image suggested dust particles were moving at approximately 20 meters per second, considerably faster than the rotational velocity, but consistent with gas drag. This is where the situation becomes particularly intriguing. If dust particles are ejected at 20 meters per second by carbon dioxide outgassing, and if the object is losing 129 kilograms per second of carbon dioxide, as measured, then the dust production rate should be substantial, likely measured in tons. Such a quantity of dust ought to generate a prominent, extended tail readily visible in professional telescope imagery. However, the July Hubble image showed no such tail, only the forward glow and a diffuse coma. One possibility is that the dust particles are so minuscule that they are propelled forward by radiation pressure before they can coalesce into a conventional tail. Solar radiation pressure can accelerate extremely small dust grains more rapidly than gravity pulls them inward. If the dust grain size is less than 1 micron, radiation pressure becomes the dominant force, potentially pushing the particles ahead of the nucleus. However, this would result in a forward tail, not a forward glow. The morphology is incorrect. Another hypothesis suggests that the dust particles are electrostatically charged by solar ultraviolet radiation and interact with the sun's magnetic field. Electrically charged dust behaves differently from neutral dust, exhibiting susceptibility to focusing or dispersion by magnetic fields, which could produce unusual formations. NASA's SPECS survey adds further complexity to the puzzle. It detected 3 Atlas as a point source in the infrared spectrum, exhibiting no extended emission, no coma, no tail, merely a solitary dot. In contrast, Hubble clearly observed extended structures. The discrepancy lies in the wavelength of observation. Hubble observed in visible light, while SPECS operated in the infrared. Dust reflects visible light but emits thermal infrared radiation based on its temperature. If the dust surrounding 3 Atlas is exceedingly cold, colder than expected at its distance from the sun, it would appear dim in infrared, even if luminous in visible light. This implies that the dust is not efficiently absorbing solar heat. It might be highly reflective, deflecting light before it can be absorbed, or it could be composed of materials with atypical thermal properties. The nature of the tail will become clearer in December, when 3 Atlas reappears from behind the Sun. Subsequent observations from multiple telescopes across various wavelengths will reveal whether the tail has further developed, if it conforms to typical cometary tails, or if it continues to display unusual characteristics that defy current models. Chapter 9. The 1 in 500 Trajectory Coincidence. 3 Atlas traverses a retrograde orbit inclined at approximately 175 degrees relative to the ecliptic plane. While this sounds extreme, its practical implication is that the object is moving almost precisely within the plane of planetary orbits, but in the opposite direction. It navigates the solar system along the same flattened disk occupied by Earth, Mars, Venus, and Jupiter, albeit in reverse. The likelihood of this occurring randomly is estimated at 1 in 500. Most objects originating from interstellar space are expected to enter the solar system from random directions, as space is three-dimensional with no preferred orientation. If interstellar comets are merely debris ejected from distant star systems on random paths, they should arrive from all angles, above, below, or from the sides, uniformly distributed across the celestial sphere. However, 3 Atlas entered the solar system with an alignment nearly parallel to the planetary orbits, deviating from the ecliptic plane by only 5 degrees. While not impossible, this is highly improbable. Furthermore, it's not solely the inclination that is noteworthy. The trajectory brings 3 Atlas into close proximity with several planets. It will pass within 30 million kilometers of Mars on October 3rd. It will also pass within a reasonable distance of Venus. And in March 2026, it will approach within 54 million kilometers of Jupiter. Individually, these close encounters are not extraordinary. Space is vast, and many orbits intersect planetary proximity without deliberate targeting. However, the combination of ecliptic alignment and multiple planetary encounters significantly reduces the probability of such an event occurring by chance. Loeb calculated the combined odds of all these geometric factors, aligning randomly to be approximately 1 in 500. While not impossible, this probability is sufficiently suspicious to warrant consideration of non-random explanations. If 3 Atlas were a deliberate probe sent to survey the inner solar system, one would anticipate a trajectory that passes near the major planets and aligns with the ecliptic plane, as this is where significant activity occurs. The rocky planets, most moons, the asteroid belt, and regions where life might potentially arise. A surveyor probe would naturally follow such a geometric path. Critics contend that this is a case of selection bias. We are only noticing 3 Atlas because its trajectory brought it close enough for detection. It is possible that hundreds of interstellar objects are traversing the outer solar system on random trajectories, remaining undetected due to their extreme distance and faintness. The objects we detect are, by necessity, those that pass close to the Sun and Earth. This argument holds merit. Our observational capabilities are heavily skewed towards objects traversing the inner solar system, where our telescopes are concentrated. We may be missing the vast majority of interstellar visitors that remain in the outer regions. However, this does not account for the specific alignment. Even among objects that approach the Sun closely, most would not be aligned with the ecliptic. They would typically possess high inclinations, diving through the planetary plane at steep angles. The near coplanar trajectory of 3 Atlas with the planets is unusual, even within the subset of detectable objects. Another aspect of the trajectory warrants attention. 3 Atlas is on a hyperbolic orbit with an eccentricity of approximately 6.16. This indicates it is moving well above escape velocity, meaning it is not gravitationally bound to the Sun. It originated from interstellar space and is returning to interstellar space. However, the trajectory can be extrapolated backward. By reversing the orbital mechanics, astronomers can determine its original point of origin. Calculations suggest it originated from the thick disk region of the Milky Way, possibly from a star system between 7 and 11 billion years old. This age is incredibly ancient, predating our Sun and solar system. If 3 Atlas formed around such an old star, it has been traveling through space for potentially billions of years. The accumulated cosmic radiation exposure, chemical alterations, and sheer age make it unlike any object previously studied. Its galactic path also offers clues. Based on its velocity minus the Sun's gravitational acceleration, 3 Atlas was traveling at approximately 58 kilometers per second through interstellar space before entering our system. This speed is consistent with objects from the thick disk population. What is inconsistent is the timing of its arrival. 3 Atlas entered the inner solar system in mid-2025, precisely as our detection capabilities reached a level sufficient for its observation. The Vera C. Rubin Observatory became operational, Atlas reached full functionality, and SPEX was launched. All the necessary infrastructure to characterize an interstellar visitor was in place. Is this a coincidence, or is it a deliberate timing? If an advanced civilization intended to dispatch a probe to survey our system, they might strategically choose their arrival time. They could wait until the target civilization has developed sufficient technology for detection and study, arriving when telescopes capable of compositional analysis and trajectory measurements are available. This would enable first contact when the recipients are equipped to comprehend what they are observing. This scenario, while sounding like science fiction, is not entirely implausible. Any civilization capable of interstellar travel would likely possess the means to observe target systems from afar. They could monitor for technological signatures such as radio transmissions, artificial lighting, or atmospheric pollution, indicators of a civilization reaching a certain developmental threshold. Earth has been broadcasting radio signals for over a century. Our technological signatures have been detectable by external observers for decades. If 3 Atlas were dispatched in response to these detected signatures, its arrival timing would be logical. Of course, this presupposes the feasibility of interstellar travel, the capacity of a civilization to traverse light years of space, their intention to send an object here, and their decision to disguise it as a comet. These are numerous assumptions. However, the trajectory remains a 1 in 500 probability, perfectly aligned with the planetary plane and featuring close approaches to multiple worlds, arriving precisely when we developed the capability to study it. The encounter with Jupiter in March 2026 will be a decisive factor. If 3 Atlas maintains its predicted trajectory, passing Jupiter at the expected distance without deviation, it would support a natural explanation. Orbits governed solely by gravity are predictable and uneventful. However, any deviations, any changes in trajectory inexplicable by gravitational perturbations from planets, would present a significant problem. We would then need to explain what altered its course, and natural explanations quickly become scarce once gravity and outgassing are ruled out. Chapter 10. What happens next? The verdict draws near. October 3rd, 2025 is tomorrow. The high-risk camera will be directed towards 3 Atlas as it passes at a distance of 29 million kilometers, offering a resolution of 30 kilometers per pixel. This level of detail should be sufficient to differentiate the nucleus from its dust cloud and to estimate its actual size. If the nucleus is confirmed to be 5 kilometers or larger, the statistical anomaly becomes impossible to disregard. We should have detected thousands of smaller interstellar objects before encountering one of this magnitude. The natural explanation would necessitate an increasingly improbable series of coincidences. ESA's Mars Express and ExoMars Trace Gas Orbiter will conduct simultaneous observations using spectrometers and cameras, employing multiple wavelengths, instruments, and perspectives. Combined, these Mars missions will provide the most detailed examination of an interstellar object ever undertaken by humanity. Additionally, we will be searching for precursor probes, objects traveling ahead of 3 Atlas that might reach Mars while we are observing the main body. HiRISE will scan the surrounding space. If anything anomalous appears, if multiple objects are detected instead of one, the conversation will shift immediately. Then a period of waiting ensues. 3 Atlas will disappear from Earth's perspective behind the Sun in late September, obscuring our line of sight. The object will reach perihelion on October 30th, its closest approach to the Sun, hidden from our telescopes by 150 million kilometers of incandescent plasma. This will be a 2-month period of blindness, 2 months during which anything could transpire unobserved. Trajectory adjustments, probe deployments, fragmentation. Whatever occurs during this window will only be revealed in December upon the object's reappearance. December 3rd is the projected date for ground-based telescopes to reacquire 3 Atlas. Amateur astronomers worldwide are preparing, and professional observatories are scheduling observation time. Every entity desires the initial observation of the object returning from perihelion. All will be comparing pre-perihelion data with post-perihelion observations. Has its brightness changed? Has its outgassing increased or decreased? Most crucially, is it where calculations predict it should be? If 3 Atlas emerges on a different trajectory, if its orbit has shifted in ways inexplicable by gravitational interactions with the Sun and planets, that would constitute evidence of propulsion, evidence of technology. At that point, even the most skeptical will be compelled to consider alternative hypotheses. The object's chemistry will also offer further clues. New spectroscopic analysis in December will determine whether the nickel without iron signature persists, if the dominance of carbon dioxide continues, or if new emission lines appear that were not present before perihelion. Thermal processing due to solar heating might alter surface chemistry in detectable ways. If the object fragments, that would actually support the natural comet hypothesis. Natural comets occasionally disintegrate near perihelion due to thermal stress. We have witnessed this with comets like Shoemaker-Levy 9 before its impact with Jupiter. Fragmentation would be considered normal unless the fragmentation appears controlled. If multiple pieces separate cleanly and proceed towards different destinations, then fragmentation could be interpreted as deployment. The Jupiter encounter in March 2026 is another critical event. NASA's Juno spacecraft, currently in polar orbit around Jupiter, could potentially observe 3 Atlas as it passes within 54 million kilometers. Juno is equipped with cameras, spectrometers, and particle detectors, instruments designed for Jupiter studies, but capable of characterizing this visitor. Discussions are underway regarding whether Juno could maneuver for a closer observation. The spacecraft has limited fuel, and its mission has a planned endpoint. Diverting that fuel to pursue an interstellar object instead of studying Jupiter would be a contentious decision. However, if the October and December observations reveal truly anomalous phenomena, the scientific justification for redirecting Juno would become compelling. ESA's JUICE spacecraft will also attempt observations in November, though the data transmission will be delayed until February 2026 due to communication constraints. JUICE is positioned further from Earth, on the opposite side of the Sun, using its antenna as a heat shield, limiting data transmission until its orientation is adjusted. Therefore, we are accumulating observations over several months, from multiple spacecraft at various locations within the solar system. By the spring of 2026, we will possess the most comprehensive dataset ever compiled for an interstellar object. This dataset will either confirm 3 Atlas as an extraordinary but natural comet originating from another star system, or compel us to seriously contemplate the possibility of visitation. The scientific community is preparing for both outcomes. In private conversations, the astronomical community is actively contemplating the necessary protocols should evidence of artificial origins be definitively established. Questions arise regarding who would make such an announcement, how to rigorously validate extraordinary claims before public disclosure, and what the implications would be for planetary defense should additional extraterrestrial objects follow. There is no established procedure because this particular scenario was not seriously anticipated. Existing protocols for the search for extraterrestrial intelligence primarily address radio signals and deliberate transmissions, rather than physical entities that initially appear to be comets. The closest precedent involves the established methods for announcing the discovery of life on Mars or Europa, which mandate thorough verification, peer review, and multiple independent confirmations before any official statement is made. However, these procedures are designed for analyses that can extend over months or even years. Given that 3 Atlas is currently transiting and on its trajectory out of our solar system, swift decisions are essential for any meaningful study. Some researchers are proposing an interception mission. This would involve launching a small probe to intercept 3 Atlas before it travels beyond Jupiter's orbit. The objective would be to capture high-resolution imagery, collect samples from its outgassing plume, and measure its magnetic fields and particle emissions at close range. The primary challenge lies in the timing. Even a rapid spacecraft would require several months to achieve a rendezvous. By the time authorization and funding were secured, and by the time the probe itself was constructed and deployed, 3 Atlas would have long since departed. Interstellar objects traverse vast distances at considerable speeds. Opportunities for observation are measured in weeks, not years. This underscores the critical nature of the period between October and March. It represents our singular chance to gather crucial data on the 3rd confirmed interstellar visitor before it recedes into the immense void between star systems. After March, it will be too distant and too faint for detailed observation. We will observe its gradual disappearance into the cosmic expanse, meticulously extracting every piece of information attainable from the data we have managed to collect. And then we will wait. We will wait to ascertain if our analyses reveal naturalistic explanations for all observed peculiarities. We will wait to see if further interstellar objects arrive exhibiting comparable traits. We will wait to determine if the statistical probability either resolves or escalates. And we will continue to ponder, even if the collected data ultimately substantiates a natural origin, even if every unusual characteristic finds a conventional scientific explanation, we will still wonder. This is because a 60% probability of technological origin implies a 40% probability of a natural one, and 40% is not an insignificant figure. The universe has a history of surprising us. Phenomena such as black holes, dark energy, exoplanets, and gravitational waves each represent discoveries that unveiled aspects we had not predicted, and for which our understanding was rudimentary. 3 Atlas could represent another such surprise. It might be something natural, but so exceptionally unusual, so profoundly unexpected, that it compels us to revise our scientific models and broaden our conception of what is possible. Alternatively, it could represent the most momentous discovery in human history, the first definitive confirmation of contact with technology originating from beyond Earth. Evidence that humanity is not alone, proof that other civilizations exist, and that some among them possess the capability for interstellar travel. The answers are forthcoming. The data is being acquired. October 3rd, December 3rd, and March of the year 2026 are 3 specific dates that hold the potential to fundamentally alter our understanding of everything.